I'd like to make an analogy that hopefully will resonate with us. We all recognize this as our valley. We're lucky to live here. Suppose we start here on campus and a magical, mystical plane, we can't understand how it works, takes us to the top of the mountain and drops us off. Now that magical, mystical plane that we can't possibly understand has magically delivered to each of us gravitational potential energy. And the average amount of gravitational potential energy per person is going to be the mass of the average person, 75 kilograms, not me, times g, times the height, and the magical plane took us up 1,000 meters. So that means on average, we have given each person, the plane has, 750,000 joules of gravitational potential energy. Now, the easiest way to get back to campus is along the ridge, over the M, and down Rouse Street. And the question is, what would be the change in gravitational potential energy along that path? Negative 750,000 joules for each person on average. Okay? What goes up must come down. If you're ending up in the same location you started, you had to have just as much elevation drop as you had elevation gain in the magical plane. Now, that is a nice, easy path, but it's not the only path that is going to get us back to campus. Most of us are going to take that easy path, but not Valerie. Valerie sees that there is another way to go, and so she chooses this path here. Okay? Now, what is going to be the change in gravitational potential energy per person along that path? Yeah, the same. Still negative 750,000 joules for each person. Okay? Now, because that path along the ridge is the easy path, the low resistance path, we get most of us going that way, a high current, a high flow, if you will. On the hard path, the high resistance path, we only get Valerie going that way. It has a small current going that way. Now, folks, my question to you is this. Where is the plane?
Battery.
The battery. Instead of taking people to the top of a mountain, it takes coulombs to the top of an electrical mountain through a process that we cannot possibly understand unless we are in the chemistry building. It is mystical. Okay? It involves chemistry. Now, once we get to the top of the cliff, we don't all have to come back to the bottom of the cliff along the same path. Okay? Now, which is the easy path? Yeah, this one's the easy path, and this is the hard path down the cliff. But they both get us back to campus, do they not? Now, how bright are the bulbs? Well, I got a really bright bulb with two dim bulbs here. Now let's think about why they're bright, okay? One way to think of it is the voltage. If I measure the voltage across the battery, I get 12 volts. If I measure the voltage across that bulb, I get 12 volts. If I measure the voltage across that dimmer bulb, I get 6 volts. And that's always, always, always going to be the case. When you have identical bulbs, and those are the only kind we'll use in this class, when you have identical bulbs, if one is bright and one is dim, there will always be more volts across the brighter bulb. Now, let's look at current. Well, the fact that this is a brighter bulb means there's more current going through it. The fact that these are dimmer bulbs means that there's less current through it. This is the entire class except for Valerie This is Valerie, and the current through the battery, the people that got on the plane, all y'all. Okay? All y'all. Okay? Everybody in the class. Now, suddenly we see that there's two ways to interpret a brighter bulb. More flow, more glow means that the brighter bulb has more current going through it. If it's brighter, it also has more volts across it. We say more volt, more jolt. We tried to find something a little bit catchier than that, but that's the best we could do. Okay? Now these are not unrelated. The voltage difference across the bulb is what's driving the current. That's what's pushing it through the bulb. If I've got more volts across the bulb, I'm driving more current through the bulb. Okay? So they're not unrelated. Now, our current model took us a long time to develop. It had a lot of different bits and pieces. It was fairly complex. The voltage model is just trivial by comparison. This is all that's there. Voltage is how much energy, electric potential energy, that a Coulomb gains going through the battery or loses going through a bulb or a resistor. Now folks, we want to be really careful with our language. I'm careful with my language. I ask you to be careful with your language as well. Whenever we're talking about voltage, we really mean voltage difference from point A to point B. And so when we're talking about voltage, it's always the voltage across the bulb, from one side of the bulb to the other. It's the voltage across the battery, from the negative terminal to the positive terminal. When we talk about current, it's the current through the bulb. It's the current through the battery. Now when we get to that next midterm, I'm going to instruct my graders, any sentence that has volts and through in the same sentence, we're just going to scratch it out and not grade it. It's as if you never wrote it. Okay, we'll throw it away. Okay, we're almost done with this model. More voltage, more glow, or more volt, more jolt. The brighter the bulb, the more volts across it. And this is the last piece. What goes up must come down. The voltage rise across the battery is going to equal the voltage drop around any path from one side of the battery to the other. Just like you can't go to school and back and go uphill more than you come downhill, the same thing is true when you go around a complete circle in an electric circuit. You can't go up more volts than you come down. It's impossible.